This is Module 13 of an Introduction to Engineering Vibrations, Single Degree of Freedom Systems. Today's learning outcomes are to define what's called the natural frequency and the period of oscillation. This is where we've left off. We now have the differential equation of motion, or what we abbreviate as the DEOM for this vibratory system, and we've come up with the general solution down here. Now, from that general solution, we see that we have an argument for the cosine and the sine square root of km over t. Square root of km is called the natural frequency. And so it's defined as the natural frequency. That's why I have the 3 equal sign there. And it's given in radians per second. Then we have what's called the also the natural frequency, but it's in cycles per second, or hertz. And so that's 2 pi, or excuse me, omega natural over 2 pi. And then we have what's called the period of oscillation, and that's defined as the fundamental period of oscillation, and it's given the symbol tau, and it's 1 over the natural frequency in hertz, or 2 pi over omega natural. And so that's the time for each cycle to occur, so it's in seconds. So now let's do a worksheet together. For the vibratory system shown here, we want to find the natural frequency and the period of oscillation in terms of the mass, K sub A, K sub B, K sub C, and K sub D for the 4 springs. First of all, we can see that K sub C and K sub D are in series. And we know how to combine springs in series. And so let's call it K sub CD equivalent is equal to K sub C, K sub D over K sub C plus K sub D. Okay, and now we can see that K sub A, K sub B, and this new equivalent, K sub CD equivalent, are all in parallel. So K sub A, K sub B, and K sub CD are parallel springs. So they're in parallel. And so the overall K equivalent now is equal to K sub A plus K sub B plus K sub C, K sub D over K sub C plus K sub D. And so we now have we can find the natural frequency. Omega natural is equal to the square root of K over M, so that's going to be K sub equivalent over M, or the square root of K sub A plus K sub B plus K sub C, K sub D over K sub C plus K sub D. And so that is the natural frequency. So we'll underline that with our answer. And then to find the period of oscillation, it's given the symbol tau, and it's 2 pi over omega natural. So for this particular system, tau or the period of oscillation, equals 2 pi over the square root of k sub A plus k sub B plus k sub C, k sub D over k sub C plus k sub D. And so that's a quick example of how to find, for a particular vibratory system, the natural frequency and the period of oscillation. And so that's a summary of today's module. We defined the natural frequency and the period of oscillation and actually did a short worksheet to show how to calculate those. And I'll see you next time.